Welcome to AHA Math and Science. In this video, we're going to discuss the physics behind Titanic sinking. So on April 15th, 1912, a tragic event happened. The RMS Titanic sank in the North Atlantic after striking an iceberg during its maiden voyage from Southampton to New York City. Of the estimated 2,224 passengers and crew on board, more than 1,500 lost their lives, making it one of the deadliest peacetime maritime disasters in history. So in this video, we're going to discuss some of the simple physics that Captain Smith of the Titanic should have known so that this tragic event could be avoided. So let's first look at some of the facts about the ship. So the Titanic weighed over 46,000 tons, and its top speed was 23 knots. And when her lookouts sighted the iceberg, the ship was traveling about 22 knots, just a little below the top speed. Also, according to Wikipedia, an underwater spur of ice scraped along the starboard side of the ship for about 7 seconds. So these 7 seconds can be considered to be the time of a collision when the Titanic collided with the ship. And furthermore, the damage to the hull consists of 6 narrow openings covering a total area of only about 12 to 13 square feet, which is equivalent to 1.1 to 1.2 meters square. So this is a very small area during the impact. And because the openings are long, but they are very narrow. So the total area is rather small. So these are the key information: the mass of the ship, the speed of the ship when the collision happened, and the time of collision or the duration of collision, 7 seconds, and then the impact area. These are all the information we need to know in order to actually do simple calculations to figure out the physics behind the sinking of the Titanic. So the first concept we're going to explore is called momentum. So what is momentum? Momentum is defined as a product of mass times velocity. And the momentum of an object can be changed when a force is exerted on it. So according to the impulse momentum theorem, on the left side, we have the force times the duration of the collision. This is known as the impulse. On the right-hand side of the equation, we have the change of momentum. The mass times the final velocity is the final momentum, and the mass times the initial velocity is the initial momentum. So this is the change of momentum. So for example, a ball strikes the floor and then rebounds. You can think about it has initial momentum, which is negative because the ball is moving downward. And after it strikes the floor and rebounds, now the final velocity is upward, so it's positive. So there's a change of momentum. And this change of momentum is due to the fact that the floor exerts an upward force on the ball. So this is an example of the impulse momentum theory. And the same thing happened here during the creation of the ship with the iceberg. So the ship is moving with a very large velocity, about 22 knots. So the VI is huge. And the final velocity is rather small because the ship has slowed down significantly after collision. So we can kind of think about the final velocity to be almost zero. And so the force has to be exerted by the iceberg on the ship. And the duration is also known that it's very fast. It's only lasted for about 7 seconds. So with this information, we cannot do the calculation. So the mass of the Titanic is about 46,000 tons, or 4.6 times 10 to the 7 kilograms. And the initial velocity is about 22 knots or 25 miles per hour, or converted to meters per second, it's about 11.2 meters per second. And the final velocity can be taken to be zero as the ship has slowed down significantly after collision with iceberg. So with this information, we can do the calculation. Before doing that, I want to make a note that the ship has an enormous initial momentum. So it's actually equivalent to that of a 3,000-pound car that is traveling at the speed of 900,000 miles per hour. So that's a huge momentum just due to the sheer mass of the ship. So now, using the impulse moment theorem, since the final velocity is almost zero, this term can be dropped. So the force can be just figured out by using m times the initial velocity divided the duration of accretion. So plugging in the numbers, we can find the force to be about 7.0 times 10 to the 7 newtons, or 70 million newtons. Again, we have used the information from Wikipedia. The time of accretion only lasted for about 7 seconds. Now, it's not just this huge force that actually determines the damage to the ship. It involves another concept called pressure. So this is a schematic of the accretion, and the iceberg that thought to have been hit by the Titanic is kind of shown in this picture and taken by another crew member on another ship on April 15th. So you can see the iceberg has all these sharp edges. And in fact, according to Wikipedia, the damage to the ship was done by these underwater ice spurs that are very sharp. You can think about these ice spurs are just like a knife. And we know that when one wants to cut a piece of cheese with a knife, it's not just the amount of force determines the cutting, but also how sharp the knife is. So this is related to a concept called pressure. So pressure determines whether the knife can break through the surface of the cheese or not. And it is proportional to the force applied, but inversely proportional to the area of the contact area of the knife. So that is determined by the edge of the knife. Since these ice spurs are very sharp, so the contact area is rather small. As stated previously, it's only about 1.1 to 1.2 meters squared. When using the force we figured out previously, we can find the pressure. So 7.0 times 10 to the 7 newtons divided by 1.15 meters squared, that's the impact area. We find the pressure is enormous. It's actually 60 million pascals. So convert that to actually atmospheric pressure, we find this is equivalent to 592 atm. And or using another unit for pressure, pounds per square inch. This is equivalent to exerting a force of about 8,700 pounds onto a small area of 1 square inch. So this is a huge pressure. In other words, once the Titanic is hit by the iceberg, the damage is going to be inevitable. So the question really is like, how can you avoid the striking of the ship by the iceberg? So this requires one to spot the iceberg early on. And this has to do with another concept we call buoyancy. So let's analyze the forces exerted on the iceberg. First of all, there's always this downward force of gravity, Fg, which is equal to mass of the iceberg, times the gravity constant G, which is 9.8. And so the mass of the iceberg is equal to the density of iceberg times its volume, Vi. The I here stands for iceberg. The iceberg also experiences upward buoyancy force, which is equal to the density of liquid, which is just the density of seawater, loss of W, and times the gravity constant G, times the volume of the submerged portion. This is based on the Archimedes principle. So we now can analyze what percentage of the iceberg is actually below the water. Since the two forces acting on iceberg and the iceberg is in equilibrium, so the two forces must be in balance. So the buoyancy force is equal to the force of gravity. And using the expressions here for the force of gravity and the force of buoyancy, we can equalize these two terms. And once we cancel the G constant, since it appears on both sides of the equation, we can find the ratio of the submerged portion in terms of the total volume of the iceberg. So the portion submerged to the total volume of the iceberg is actually equal to the ratio of the density of iceberg, loss of I, over to the density of the seawater. Now the ice usually has a smaller density than water. So that's about 917 kilogram per meter cubic. Or the density of seawater is slightly more than the density of fresh water. So it's about 1,030 kilogram per meter cubic. In the math, we find this ratio is about 0.89. In other words, 89% of the iceberg is actually below the water, is submerged in water. And this is actually known as what? The tip of iceberg. So there's a huge piece of ice that lurking below the surface and can be actually quite further away from the surface part. The surface part is here, but the iceberg could be way further away from the surface part. So this means that in order to avoid the Titanic being hit by iceberg, the crew member must be on the lookout for this iceberg that seemed to be far away, because the underwater part could be actually very close by to the ship. And obviously the Titanic should have actually slowed down in this area known as iceberg area. So if the Titanic is traveling at a slower speed, then it's going to have a smaller momentum, then the force of impact will be smaller. Then even the iceberg, hits the Titanic, the damage will not be that severe. So basically, these are the two sort of key things that the Titanic crew member should actually watch out. So I guess if Captain Smith of the Titanic have actually kind of known the physics discussed in this video, which is momentum, pressure, and buoyancy, then this really tragic event could have been avoided. So I hope you have enjoyed this video, and thank you for watching.